welcome to this session on FMI. We'll start right away with the presentation from Andreas Pfeiffer. Andreas Pfeiffer is from DLR, background in mathematics, and is working on integration algorithms, nonlinear optimization, modelic FMI, and also eFMI. So please, Andreas.
Yeah, thank you very much. Yeah, welcome to my talk. This is a joint work together with my Bosch colleagues, Fabian Jamulowitz and Christian Bertsch, and also with my DLR colleague, Christoph Winter. And the introduction is a typical application at Bosch is to outsource computational intensive functions from the car electronic control unit to cloud computers, maybe edge cloud, and that has a very fast communication connection to the cars. And the main advantage of cloud computers, of course, is the computational power, and that can be handled very flexible. And a typical or important example is to use nonlinear optimization, maybe driven by model predictive control. And so we searched for a tool chain for optimal control problems in this area, because optimal control is the main part of a model predictive control problem. And we selected CasADi because it is an open source tool that has that uses algorithmic differentiation. It has the possibility to generate self-contained C code. It has interfaces to many numerical algorithms, and it also has interfaces or interface to FMI, which is rather new. And that was very important for us because then we are able to model our prediction models with, for example, Modelica, and use existing libraries and don't have to do everything from scratch. But that was very important. And so we analyzed and tried to look at this tool chain. So what we did, we established a framework in our study. The first part was the CasADi, we call it the CasADi native toolchain. This is just without FMI. We use the Python interface. We model or implement the prediction model in Python, and then use CasADi to formulate the optimal control problem and solve it with the solver. And then it would also be possible to apply it on a specific target, but that was not the goal of this study. And the second part we are interested is that we use Modelica models for our prediction models and export them by Daimler and OpenModelica to FMUs. And what we did is that we made a framework that uses both. And so we can compare the results and also the execution times when doing it natively in Python and CasADi, and or when we do it via FMUs. So this is the goal of our study, to look at the tool chains and compare it for industrial applications. So let's start with a remark to the FMU export from the Modelica model. We used FMI for model exchange version 2.0 because that was the version that was fully supported by CasADi when we did the study. And it's important for optimal control problems that are solved by CasADi to have rather smooth functions that were generated within the model. This is this function f for the dynamics and the function h for the output variables. And what we want to have is the analytical derivative of these functions regarding, well, with respect to the state set and the inputs u. And to get this most accurate solutions here, we have to activate some flags one flag in Daimler and also a compiler option in OpenModelica. And then or CasADi is able to use the FMI to get the directional derivative function to evaluate these derivatives. It's also important to have the correct structural dependency information in the model description XML file that is contained in FMU. That means on which variable depend these functions f and h, because this is exploited then later on in the second derivatives of this function in CasADi. Okay, let's start with the first use case. We analyzed two use cases. The first one, we selected a simple vehicle model, a single track model. As prediction model, we have a vehicle with two tires. Only the front tire can be steered. And we have 7 states for this system, some angles and rates, and the velocity of the center of gravity, also with the planar position X and Y. And as inputs, we have the longitudinal acceleration and the steering rate. And we have one output variable, the lateral acceleration. So here, just to see the equations, here is sorted Modelica code of this model, just to get an impression. This is a well-known model, and we use it as an use case, the first use case. So what we saw now is, the prediction model that we implemented in Python, and we also implemented it in Modelica and exported it to FMU. And the second part was to formulate an optimal control problem in CasADi and discretize it and solve it. So this comes now. Our optimal control problem was to follow a given trajectory in the X and Y plane. Here this U-turn starting at 0, 0 and 0, 0 and going to this point. And the optimization problem was to minimize the distance between our position X and Y of the vehicle with respect to reference positions of this reference path. And we also needed some constraints, box constraints for the inputs and also for some states. We had constraints regarding some algebraic variables, especially the accelerations here and also the overall acceleration due to the friction circle. And of course, we had the dynamics that were implemented in Python and in Modelica and exported to an FMU. And the discretization of this optimal control problem, we used a collocation approach according to an example code that was provided in CasADi. Just a few remarks to collocation. Okay, when we have a dynamical system like this, collocation means that we approximate our solution states with piecewise polynomials, pk, on the time grid, so on time intervals. And we want to have the so-called collocation conditions. That means these polynomials have to fulfill the differential equation from here at intermediate points, the so-called collocation points that are described here by this constant CCJ between 0 and 1. And we also have a continuity condition between all these intervals. So we have a lot of conditions, and we have one big optimization problem. And the optimization variables are the discrete constant control inputs, UK, and also the state values at each collocation point. So when we look at our constraints that we have formulated a slide before, then we have to evaluate all these constraints at this time grid. And additionally, we get a lot of equality constraints coming from these collocation conditions. So that's very typical that we have a lot of equality constraints for a collocation-based optimization problem. In Python and CasADi, this roughly looks like that. The first part is just loading the FMU and getting this function. That's rather simple because this interface is so nice. And the remaining part is independent on if we are, or if we have a FMU for the prediction model or the Python model itself. And there we have to define all these optimization variables as symbolic variables, and then formulate all these conditions. And finally, we can instantiate a solver object to solve this large optimization problem. Here we used IP-opt solver. That's a very well-known and established sparse matrix solver. And finally, we can start the optimization process and get the solution. So we did that for this use case. And what you see here is the vehicle position compared to the reference position. And you see, okay, that's great. We have a maximum position error of 5 centimeters. We also checked if all these constraints are fulfilled. And so we have a valid solution in all our cases. And here, this is the most important slide for this use case. That was what we are interested. We varied the optimization problem by selecting a different number of intervals. So the discretization size is changed. So we can scale the optimization problem up to 75,000 optimization variables and also the same number of constraints. And then we used different versions of the prediction model. That means, okay, first we took the Python model itself as a reference, and also FMUs generated by OpenModelica and by Daimler. And we compared the solution of this optimal control problem for these different variants for a fixed n. And we saw, okay, there are only very, very small deviations. That means we can compare the execution times of these solutions. And what we see here is, okay, for increasing number of intervals, the execution time is increasing. That's clear because the dimension of the optimization problem is increasing. And there's also a difference between these different models. We see a factor of 1.3 for OpenModelica FMU and a factor of 1.7 for Daimler FMU. And we didn't try to optimize something on the tools for the FMUs. We just used the default settings of the tools and exported the FMUs. Only this flex I have shown a few slides before we said. Okay. So the second use case we applied was a use case by Bosch, where a chiller system or multi-chiller system is used to optimize the power consumption. That means a building here is cooled by some chillers, and we looked at the chiller subsystem with 5 chillers here, and the water is flowing through the chillers. The chillers cool this water and supply a mass flow back to the building. And the goal here is to minimize the electric power consumption of all these chillers. We have some constraints here. The demanded temperature that is given here of the final mass flow and the supply temperature of the mass flow should be below. That means, okay, the building is cooled sufficiently. Then we need some additional constraints regarding our model here, because the output temperature should be below the input temperature. That means that it's here really cooling and not heating up something. And the prediction model itself has 5 states, 10 inputs, temperatures, the set temperatures for each of the chillers and the mass flows, and 7 outputs. The model itself here that was implemented in Python and also in Modelica has about 250 lines of code, just to give an impression of the complexity. Okay, we applied our framework to this second use case. and got the following results. Again, we varied the optimization problems by varying the number of prediction intervals. So we can scale up to 3,500 optimization variables. We also checked for fixed n if the solutions are similar, and that's the case here. So we can compare the execution times. And we see a factor of 1.9 for OpenModelica FMU in comparison to the native implementation in Python, and a factor of 3.3 for the Daimler FMU. And we did try to analyze a bit further where these time factors came from. And therefore, we used a nice feature of CasADi where some details is given regarding the execution times of different parts of the problem. So we can, for our optimization problems with an objective function J and some constraints G, depending on the optimization variables X, we can look at the execution times of the objective function and constraints overall solving a complete optimization problem. Okay, the time factor when we compare FMU-based optimization and CasADi native implementation for this evaluation of the objective function and constraints is about 1, so that's great. And also the optimization algorithm itself is also, there is no difference. When using FMUs, that's also great. And when we look at the derivatives of these functions, then we see for the first derivatives that are computed here, yeah, it depends on the use case and also on the size of the optimization problem. We have a factor between 1 and 2.5. And no, that's getting worse for the second derivatives. Here it depends on the use cases and so on. Factor between 3 and 10, and also for the collocation methods between 3 and 10. And we also had an implementation for using single shooting for this chiller system. Here we got a factor of 25 for evaluating the second derivatives. We have to mention that when using the CasADi native implementation, these second derivatives are computed using automatic differentiation, relying on the objective and the first derivatives. And in the FMI case, there is no information to do so. So the second derivatives are computed by finite differences. In this is done in CasADi automatically. Yeah, that's a difference in evaluating the second derivatives. And it's also important to see that these second derivatives is not only a smart part in the evaluation time of the overall optimization problem. Here for the FMU case, it's the main part. Okay, I come to the summary. We established, or we made a small framework to compare FMI-based optimal control with CasADi native optimal control. We showed it on 2 use cases, and the main results are, yes, it works very nicely, and there is a bottleneck regarding the execution times, especially for the second order derivatives. But overall, okay, there is a factor between roughly 1.5 and 3 for these use cases when using FMI. And the important advantage here is that we can use existing model libraries to model the prediction model, and that is becoming very interesting if we think about more complex prediction models. So the outlook at Bosch is that they want to continue this approach using more complex models in the building domain, to formulate, for example, nonlinear optimal control or model predictive controllers for energy-based simulations. Thank you very much.